Hello, everybody. I'll try to keep you awake for the last hour of the day and try not to talk too quickly. So for most of the past year, I've been part of a study group with the United States National Academy of Sciences and Engineering on the role of machine learning in safety-critical systems. And so I decided to try to put together a talk based on what I've learned from that experience. Most of the other members of the panel have been people who work in they're safety engineering people. Then there are just a few of us on the panel that are machine learning people. So it's been quite an education for us. Let's see, okay. So I guess I have this, right? So the talk will be in 3 parts, but basically part 1 is the majority, and then the other 2 parts are just a final wrap-up. So I thought I would start by describing traditional safety engineering as I understand it, and using as example this semi-driving on freeways. Let's see, I can... give me the... Do I get the... Oh, later. Yeah. Sorry. Yes. So I'm very inspired by this company, startup company in Toronto, called Wabi, which is led by Raquel Urtasun, who of course is from Spain. And they are working, she formerly led the group from Uber that was working on automated vehicles. And when that lab was closed, she started this new company, Wabi, that is working on semi-trailer truck driving for freeways. So in traditional safety engineering, you start by defining the intended scope of the system, semi-driving on freeways, and then you try to define what they call the operational design domain, or the operational domain. And this would, for instance, specify that we're only working on freeways, maybe only in daytime, maybe when it's not raining, some set of conditions that need to be satisfied in order to trust the autonomy to be working. And then you break that operational domain down into scenarios. So you might have scenarios where the freeway is empty, where it's very crowded, bumper-to-bumper traffic, various kinds of scenarios. And then you do what's called a hazard analysis of each scenario. So you start by identifying the harms that you're trying to prevent, things like death and severe injury and physical damage. And then the scenario might be something like I'm in the rightmost lane, a car comes in front of me and then maybe hits the brakes and slows down very rapidly. What am I going to do? Or I want to avoid a front collision, a rear collision, a side collision. I want to avoid driving off the road to avoid something. Each of these are known as hazards. So a hazard in this field is a set of states that will lead with high probability to a harm. So we go from the harms, which are kind of the results, to the set of states that would lead to that harm. And then we try to do a risk assessment. In traditional safety engineering, the focus has primarily been on the physical components of the system. What is the expected lifetime of the brakes? Or we were seeing with the water companies in these presentations, what is the age of the pumps, the age of the sewer pipes, and so on. And you estimate the probability of failure of each of the components, and then ask, does that lead to a fault, and then to a harm? I think with systems like self-driving cars or self-flying aircraft, it's much more complicated because we also have to consider the environment that surrounds the system. It's not enough to ask, well, are all the components of the vehicle working correctly, but do other vehicles do crazy things that will lead us to then have a collision, right? And so it's very difficult to do that risk assessment without first building our own control policies for how we will drive the vehicle, and then we can estimate the probability of those events occurring. But in the traditional approach, it's done at this point. And there is one of the axioms of safety engineering is there is no 100% safety. Instead, there is some socially acceptable level of risk, where risk is defined as something like the product of probability and severity, or some combination of probability and severity. And we know that, for instance, society has a much lower risk tolerance for commercial aircraft than we do for just driving on the roads. Driving on the roads, we accept tens of thousands of deaths every year, but we haven't had that many deaths in aircraft, I don't think, ever, right? 100 deaths in a commercial aircraft would be a catastrophe. So then, once you have this target level of acceptable risk, the goal is to get your risk down below that level. You now need to ask, well, given my risk analysis, do I have an easy design that can achieve that? If not, I need to add maybe redundancy. So more sensors, a backup brake system, extra batteries, whatever, all kinds of things we might want to do. And then that gives me my strategy, this mitigation development. Then, as I start to decompose the system into subsystems and subsystems, and I decompose my safety requirements into those systems too. So I need the brakes to only fail once every 10 years and something like this, right? I get set requirements for each of those. Then we get to the part that I think computer scientists are comfortable with, which is actually writing the software, building the hardware, the system design and development. Once we finish that design and development, we then need to do verification, which is to try to prove to ourselves or gain confidence that the system we have built meets the requirements, that safety requirements, and of course the functional requirements. And that typically involves some combination of testing, possibly verification, particularly for computer hardware now, like circuit design. Most of those are fully verified before they're manufactured. Software is more challenging, and there is a methodology called safety cases, where you put together carefully reasoned evidence for why you believe a particular component or subsystem is safe. There is also the need to do what's called validation. Validation is asking whether the system we've designed actually will meet the needs of the users. When I've taught software engineering, and it's not my field, the biggest thing I learned teaching it was that the number one failure mode, reason for software projects failing is that we build the wrong system because we didn't get the requirements right. So one of the goals of validation is to verify, check with the customer. The best way to achieve that is to have a participatory design where the customer has been involved the entire time throughout the process. But sometimes you have to actually do beta testing on customers to determine whether the product is really meeting their needs, as every startup company knows. Then there's the issue of maintenance and monitoring. We need to be watching the system, and we saw, again, I think the closest thing to safety engineering today is those water companies who are building IoT system sensors to monitor the entire water network, to have situational awareness about what's happening, and simulation models and so on. That's in this thing. And in some application domains, in medicine and in aircraft, for instance, there are very strict regulatory requirements for certification and documentation. Okay, so now how does this compare to what we do in machine learning? Well, the tradition in machine learning has been to just collect up all the data we can, regardless of its sources, right? Traditionally, well, tradition is maybe too fancy a word, but over the past 10, 20 years, we in machine learning and data science have been telling companies, you have all of this data that you've collected for various reasons. Maybe it's medical records for billing, or it's customer billing records, or it's customer service logs. That's gold, and we should mine it, and we can do new things with it, that were things that were not originally intended. And so we then take that data and maybe split it into a training set and a validation set and a test set, and we follow the usual machine learning methodology of training on the training set and using validation set, which is kind of misnamed, right? But to adjust our hyperparameters, and then we evaluate on the test data. But this has a lot of shortcomings, right? It does not guarantee that the operational domain, whatever that would have been, is covered. There was nothing about the operational domain here when we were collecting the data. We also don't get any kind of strong verification that the machine learned model is accurate for the safety critical system. I'm a big fan of statistical learning theory, but statistical learning theory does not give us that kind of guarantee. All it tells us is that if we are given new data points from the same distribution, then with high probability we will get them right, and with some low probability we could be arbitrarily wrong. And that's the probably approximately correct theory. And so if the actual distribution in deployment it concentrates in some region of the space that had very poor coverage, the error could be arbitrarily large. So I think the machine learning community needs to develop a new methodology in order to be fit for safety critical applications. And so I'm going to advocate something extremely ambitious, which I don't even know is possible, which is, could we achieve distribution independent accuracy? Can we get machine learning models to fit that are accurate regardless of the distribution of the queries, of the cases that we would encounter after deployment? So I think there are two steps, two processes that we need to master to achieve this. The first is we need to deliberately collect our training data to attain good coverage over the operational domain. And I'll talk a bit about some groups that have been developing risk-driven sampling techniques. So we have a solution, I think, to that first problem. The second problem is that we have to somehow verify the approximation quality of our learned models. And possibly to achieve that, we may need to collect additional training examples to fill in holes that we find in the operational domain. There, I have a proposal for an idea that might work, but now that I'm retired, I don't have any students to have make it work, so maybe someone here will be interested. Okay, so risk-driven sampling. So it has been estimated that if you just drove cars on the highways under ordinary operating conditions, you would need 9 billion hours of driving time to get good coverage of the operational domain, all of the corner cases, and so on, to achieve the sort of socially acceptable risk. And that's just too long, and you would have some very serious collisions during that process as well, so your drivers might not be too excited about that. So the approach that has been taken is twofold. First, to go and collect a substantial real-world sample of, say, driving on highways, and use that to make an initial machine learning component. But even more importantly, you use that to build and validate a digital twin simulation model. And there are still a lot of issues there about whether the simulation model will also be able to simulate the corner cases or not. But often the simulation model has a lot of knowledge of physics, so it can predict what will happen in certain kinds of collisions, even though we have no training data for those collisions. So then the strategy is to do what's sometimes called surrogate model optimization, or Bayesian optimization, right, is the other term that's used. And the idea there is that we are going to repeat this loop here, where we first fit a surrogate model, and usually we use a Gaussian process model, right? And the reason we like the Gaussian process model, here's the picture from Wikipedia of what a Gaussian process looks like, is that in this figure, the dashed line is some true function that we're trying to fit. We only have a few training data points, these dots here and here. And so the Gaussian process model fits the solid blue line. And this gray area, the Gaussian process gives us also a measure of its uncertainty at every point in the space. And it's a measure of what we call epistemic uncertainty, so which is something that's often quite difficult to achieve. And this is because the Gaussian process is one of the very few statistical models where Bayesian inference is completely tractable, right? We can get the posterior predictive distribution at any point in the space, and we can measure both our epistemic and our aleatoric uncertainty, for those of you who are familiar with with those concepts. So then once we fit this model, we use what is called an acquisition function to probe the domain in the places of maximum uncertainty. So in this case, I put these blue arrows saying, well, we should ask a query here because the model is very uncertain, and here, and so on. And we collect up a batch of those data points we want, and then we simulate them in our digital twin. We determine what the correct response or the outcome of the scenario will be, and then we use that to retrain our surrogate model and retrain our machine learning component model. And we can iterate this process until we can't find any more points where the model fails. Now, the metrics that we might be looking at are things like reasonable coverage of the entire state space and good coverage of the hazardous states. So here's an example of some work coming out of Wabi that was published in November called Adversarial Scenario Generation, or ADSIM, by Wang et al. Now, they've collected data from real scenarios, and here's one. This blue rectangle here is the so-called ego vehicle. It's the automated vehicle that we want to model. This was a bus, and this is a pedestrian who is crossing the street here in front of our car, and some more pedestrians here are walking this way. So in the original scenario, the bus was stationary, it did not move, and so the ego vehicle, I don't know if you can see there are little dots there, that indicates that the ego vehicle was slowly inching forward, moving forward. But there was time for the pedestrian to cross the street. So now, so they collect, when they collect these scenarios, they have the trajectories of all of the actors, so their locations and accelerations at each velocities and accelerations at each point along the trajectory. They have LiDAR data, which is what they primarily work with. They have a map of the streets. And then they select one or more vehicles. In this case, they're going to select the bus, and they're going to perturb it. So they're going to move the bus into this lane and have it drive away. And the perturbation is designed to cause collisions, to break the law, to make the passengers in the vehicles very uncomfortable. So it's an adversarial counterexample, basically. We think of this as a bit like adversarial machine learning. The perturbation is at the level of a kinematic trajectory. Early work in adversarial learning has always worked at the image level, right? And we're perturbing the pixels of the image. But you can't get such a big conceptual change, or moving to an entirely different lane, driving in a different direction, and so on. So they're doing the perturbation at the level of scenarios. And then having perturbed it, their proprietary expertise, I believe, is being able to now generate the LiDAR data that would be measured under that situation. So they can take the original LiDAR data and update it. And then they run their system end to end and see if it causes a collision. And in this case, when they run it end to end, now the blue car, which was waiting for the bus to move, instead moves forward and strikes the pedestrian. So it's a very serious harm, a collision there. So this adversarial process has succeeded in finding a new bad case. But they'll repeat this something like 10 times and then keep the perturbation that had the largest adversarial loss and add that to their collection. Then they'll go to another scenario, try to perturb it, and so on. So many scenarios. Here are the results. So what I'm showing here there are 3 different components to their adversarial loss, right? Collisions within 5 seconds, comfort for the passengers in the car in terms of the side-to-side comfort, and jerk comfort, which is the sudden starts, sudden stops. And they were able to increase the probability of collisions, or the percentage of collisions, by 376%. And they're without really much change here in these other 2 measures. It's interesting that although they are not deliberately trying to fool the deep learning, computer vision part that's analyzing the LiDAR point clouds, they do actually make them somewhat less accurate. So these are estimates of the F1 score for perception, and this is for predicting the future paths of the vehicles, which is another thing the system has to do. So then they can retrain the model now with these cases that they've generated. And after retraining, the percentage of collisions drops to 17%. Now that still seems extremely high, of course. And that's because here we are really enriching, focusing on bad cases. That's not what we would expect under ordinary driving conditions. So they don't report iterating this more times, but that's the basic idea. So the most important thing is their ability to make their perturbations at a kind of semantic level, at the trajectory level, rather than at the pixel level. Okay, so the second challenge, and this is the total speculation part of the talk, is can we verify the correct behavior of the machine learning component? Now, the surrogate model work that we've been doing in this part here, that's not really testing. It's slightly, I said it's sort of slightly testing the perception, but it's not really looking for weaknesses in the fitted machine learning model, right? It's really looking for weaknesses in the controller that would lead to collisions and other harms. So the problem with machine learning, of course, is that we can't guarantee what's happening in between our training data points. So here's a little toy example where the orange dots are intended to be our training examples. We have one input feature X, and this is our output value Y. And I'm just imagining that there's some bad spike that's hiding in between these two data points here, right? When you train a deep network and you're using these rectified linear units, the ReLUs, you get a piecewise linear function fit, but it can do these crazy things in between the data points. So how can we guarantee assurance that this kind of spike does not exist here? Or how can we find regions where the function is behaving badly? Well, there's a small and growing set of researchers that are looking at verification of deep learning. It started trying to verify the non-existence of adversarial attacks at the pixel level. But there's been some recent work by Singh et al., and this was pointed out to me by Zico Kohler at Carnegie Mellon, who is part of this community. And they have a technique that I think we might be able to repurpose and use here. So the idea is that suppose we consider these two adjacent training examples, X1 and X2. We're going to ask a verifier to maximize this quantity, where alpha is a number between 0 and 1, or more generally, alpha lives in a what's called now I'm blanking on the name, a probability space of all possible assignments of zeros and ones, a simplex, a probability simplex. So a one-dimensional probability simplex is just the interval between 0 and 1. And so we're asking, find the value of alpha that maximizes this difference. Now in the numerator we have f of alpha times x1 plus 1 minus alpha x2. So that's going to give us this the blue line here, right? Because we're going to interpolate x between these 2 points and then push it through the function f, and we'll get the blue line here. And then this value here is alpha times f of x1 plus 1 minus alpha f of x2. That's the orange line here that joins x1 to x2. And then we're asking it to find the value of alpha that makes the biggest absolute difference between the blue line and the orange line. And that will be presumably this value here that gives us this peak. And the point is that this team, Singh et al., has a way of solving that reasonably efficiently. It's a big question how much it will scale up. They're able to use it on things like some kinds of bag of words classifiers and adversarial examples of the traditional type, and they can do it for small computer vision problems, but we'll see. In any case, this looks great in one dimension, but images, if we have an 8 gigapixel image, trying to do this in 8 billion dimensional space would not be wise. And so I think, again, we need to be interpolating in a smart space, like the space that AvSim uses, where we're changing trajectories and positions and that's all. Because AvSim is operating in something like a 50-dimensional space, and that seems much more reasonable. So the idea would be for each known training case, identify say, the 49 most similar training examples, and then where 49 plus 1 or 50 would be the number of parameters in the scenario. And then we consider all convex combinations interpolating between those points and try to find the maximum discrepancy among them. The other thing we can do, of course, is if we can find the value of alpha that maximizes this, we can generate a new data point for that value. So I call it alpha q as my query, my new alpha, and I'll call xq the corresponding scenario that would be generated there. Again, I can now simulate what happens, and I can get the response yq. I can retrain my network, and hopefully then I can remove that spike from the fitted function by putting a data point right here that says, no, the true value of the function should be down here. How many iterations of that do we need? I don't know. Okay, so as I say, nobody has tried this yet, so maybe we'll know in a year from now whether that kind of thing works. Okay, the last thing I want to talk about in terms of traditional approaches to safety engineering is estimating the risk, that is the probability of harm under normal operating conditions. So we don't have any natural data distribution. We've deliberately generated training examples that are for all these accidents and collisions that we want to avoid. So we need to be able to simulate the system under its ordinary operating probability distribution and try to estimate the probability of harm. And so the solution is to fit a probabilistic model of what we think will happen under normal operations. So we do have training data from our driving around that can give us some idea about the probability of initial states. We can simulate with our model and get the probability of different system behaviors. And the other thing we have to do is build probabilistic models of the behavior of all the other agents, the pedestrians and the other cars and, I don't know, deer and kangaroos and whatever. Now, that's fine. That lets us simulate trajectories from ordinary operations, and we could do Monte Carlo simulation of that. But as I said before, the estimate is that we would need to do 9 billion such simulations. Okay, and so even in simulation, that's too much. So instead, what we will do is develop a proposal distribution and use a technique called importance sampling, which some of you may be familiar with. But the idea is that we're actually going to sample according to this proposal distribution Q of S, which is really the distribution we have generated that is highly enriched for bad things, for collisions and other harms. And so we're going to simulate primarily Q of S, and every time we have a collision, we will count that by not weighting it with a weight of 1, but weighting it by a weight of P of S divided by Q of S. And so the idea is that we are correcting for the fact that we're sampling according to Q of S. So if we multiply this by Q of S, we get something that's like a sample from the operational distribution. And so there's a very nice paper that just came out a few weeks ago from Michael Kochendorfer's lab at Stanford University. He has a startup company in autonomous aircraft, and they use this technique of surrogate model optimization to simultaneously discover the failure regions and then estimate the probability of failure under normal operations. And so here's the demonstration task that they use is imagine trying to visually detect the runway that the plane is supposed to land on, and in particular to find these 4 corners, these red dots here. And so they show that here's the number of samples that they're drawing using this proposal distribution, and this is the estimate of the probability of failure. And early on, it's extremely noisy, but it converges quite quickly. Maybe with 400 samples, they've already have a good estimate of 5.8 times 10 to the minus 3, which still seems rather large to me. I'm not sure I want to ride in this airplane yet. But if we had done Monte Carlo samples and done 1,000 of them, we would only have seen 6 failures, and so our estimate would be quite a bit noisier. It's on the, it's basically the right, but it would be much less confident. Okay, so with these tools, machine learning can be integrated into the safety engineering process. We talked about the design and development stage, where we're going to use uncertainty-driven or surrogate model sampling to try to find the high-risk scenarios, and then verification to verify that the machine learned model is good, and finally risk assessment. So that's fine, but one of the challenges of traditional safety engineering is that it helps us model the known hazards. But in any sufficiently complex system, there are going to be novel hazards that we didn't discover until we deploy the system, right? And so I want to talk about this work by Nancy Leveson. I think the most important book that has been written on safety engineering in the last decade or so is Nancy Leveson's book from 2011, Engineering a Safer World. And her viewpoint is that a system, including the human organizations that build and use and operate it, can be decomposed into a hierarchical set of systems and subsystems, and each of them is viewed as trying to solve a control problem. In particular, we think of say the operators of a nuclear power plant or the operators of an aircraft as the needing to maintain the safety of the system in the face of disturbances of various kinds that can occur. So, of course, some kinds of disturbances could be environmental novelty, conditions that we had never encountered before. But a more common form of disturbance is budget cuts. So, in a large company, and I won't name any names, but you can think about some companies that have been having troubles recently. There have been budget cuts and staff reductions because it's very natural, if the safety engineers have done a good job, the system operates without any adverse effects for long periods of time. And management says, why am I paying salaries to all these safety people when they don't need to do anything? The systems are working very well. The result is that over time, complex systems tend to migrate toward higher and higher risk situations. And in Nancy's book, she documents, for instance, the Bhopal disaster in India, showing that system had been, they had staffing reductions, inspectors had written alarming reports that were ignored, and so over time the system was getting to be more and more risky, and so the final person who gets blamed for the disaster was really just the final step in a series of management errors. A safe controller must detect and compensate for these disturbances, and she views this as going all the way up to the prime minister or the president, through the regulatory organizations, the commercial organizations, finally the users. So she draws a picture something like this. We have the vehicle itself with its AI controller. We have the driver under the condition that this is not a fully autonomous vehicle, but relies on the driver to intervene sometimes. We know that there are safety monitors for some of the self-driving cars. And of course, there's the system update team that releases revisions to the software, maybe also changes to the hardware, and so on. So as an AI person, the question that comes to my mind is, can AI techniques help with this process, right? Traditionally, it has only been the humans in the system that provide the adaptive capabilities of these systems. But when we think about AI technology advancing, can we detect and respond to novel risks, at least with some automated support? So one thing I've worked on in my lab a lot is detecting novel situations. So the perceptual system will inevitably encounter novelty. My favorite example is this thing called the one wheel, right, which is a kind of motorized skateboard that people ride. This wasn't around 10 years ago, right? So if we had built a system and trained it on the kinds of vehicles that existed in 2010 or 2014, we would have no training data for this. And yet people riding these behave in different ways than people riding ordinary skateboards or bicycles. There were also no e-bikes in those days. Now we have lots of e-bikes. So, and in the United States, we have people wearing novel Halloween costumes every October, and of course, there are always novel road conditions. So there's actually a company in Peru that is collecting data in Peru that they think will be novel with respect to North America or Europe. And so they have examples like this one where there's a construction site here, but instead of putting up traffic warning cones, they've put concrete blocks in the road. Here's another example of something that really could happen anywhere, where there was some kind of a banner on this overpass that's become detached in the wind and it's blowing around, right? And how is the computer vision system going to even see that and respond appropriately? So I think I don't have time to talk about that one. So we have these perception failures where it's a novel kind of object or a novel imaging condition, or we lack sufficient sensors. For instance, we don't have any, the LiDAR does not see very well the sides of the vehicle. And so there are cameras that look at the sides of some of these vehicles, but there's no redundancy. So if the camera is dirty, then there's no visibility at all. The other thing is control failures, like near misses and collisions. So one of the things that people in the safety engineering literature like to talk about is what are the sort of key performance indicators for people in safety critical organizations. And one of them is how many near misses did we detect? How many anomalies did we detect? And we should be examining those anomalies and trying to understand why they are occurring, because they're really the only kind of evidence we get of some novel way that our system might fail. Because the prior belief you have to have as operating a safety critical system is there are unknown failure modes, and it's our job to find them. And so we should be rewarding our employees whenever they report an anomaly. But it's not just that we report it, then we need to examine it and study it. And again, we've seen some presentations today where people are building the AI tools to really support that examination. First, to detect anomalies. I don't know, I think about half of the presentations today had anomaly detection in them. But then to try to do some sort of root cause analysis, understand why that anomaly is occurring. It could be fraud, we saw in some cases. It could be some novel kind of system failure. An interesting kind of near miss, though, is what I call a counterfactual near miss. Let's see, I'm going to skip through this too. We can come back to that. Counterfactual near miss. So during the design process, we have defined a whole collection of hazardous states, right? And so typically when you're engineering a system and there's a hazardous state, you leave some margin of safety because to make your solution more robust. So you know if the system ever goes inside that margin of safety, that is a near miss, and we should report that and ask, well, why did we violate the safety margin? But there's also what I call the counterfactual near miss that we've seen in self-driving cars. So suppose I'm a pedestrian and I've started to walk across the street and the self-driving car is coming straight at me. I jump out of the way quickly. The car goes by and the car says, oh, I had the 2-meter separation with this pedestrian, no problem, right? No, there was no violation of safety. But that's because I took evasive action to avoid getting hit by the car. So we need to be able to do the reasoning about when is the behavior of our vehicle forcing other vehicles to take evasive action to avoid collisions, because those are another kind of near miss. And we know from, for instance, Udaya Pearl's theory of causality that this is a so-called level 3 inference, requires that we have a very sophisticated causal model of our system. So when we think about design in order to detect near misses, we may need to add sensors to our vehicle to detect them, but we also, in some sense, need a theory of mind. We need to reason about the fact that as a pedestrian, I saw the car coming toward me and I had to get out of the way. We need to think about that. Okay, so the next question is about automated diagnosis and repair. So far we detect anomalies and near misses, but now we want to somehow reason about what may have caused them. This is an area where artificial intelligence researchers have been studying diagnosis for 40 years or 50 years, I don't know. Back in the 1970s, they built the first medical diagnosis expert systems. So I think we have a collection of tools that we could use there. We know that we need to have a causal model of the system, including the control and information flows, and we need this reasoning capability. Now the question is, what about repairs? And I'll come back to this in a moment. I think it's very tricky to imagine a system doing self-repair. But the AI system could provide the information that could then be used by the human organization to make the repairs. So for example, it could collect up the new training examples that are needed to train the system to behave correctly in some new scenario. And it could also identify a new hazard region that the system needs to avoid, that it was not previously avoiding. In fact, that one you might be able to apply in real time on the target system if you have a planner that is dynamically planning paths. You could just add it as another kind of obstacle. So, okay. So let me finally talk about safety as continual redesign. So one of the people that I am hugely like the work of is this work by Doyle at Caltech and David Woods at Ohio State. And Doyle and Carson published an important paper now, 22 years ago, on what they call highly optimized tolerances. And it's really an alternative theory of complex systems that's quite interesting in its own right. But translating it to engineering, they talk about engineered systems that are simultaneously robust and yet fragile. So they're robust to the known hazards. So imagine for a moment we have this design space here that's just the blue line. I had to do this in one dimension. So we have a one-dimensional design space, and we know about there's a hazard over here, and we know there's a hazard here. So we maybe put a margin of safety with respect to the known hazard, and then we optimize once we put in those margins of safety. I meant to have one here too. So as designers, of course, we put margins of safeties for our known hazards, but then we optimize for cost, weight, ease of manufacturing, various other engineering criteria that we're trying to optimize. And the result is that perhaps there's another dimension that we're not aware of, where there's a hazard that we are not aware of, and we might be very close to that hazard because we've been usually, when you do constrained optimization, the optimum is almost always at the boundary of the feasible region. And so the trouble is that we will be at the boundary of this feasible region that we don't even know about, which is with respect to this hazard. So that's the sense in which engineered systems can be simultaneously robust to the known hazards and yet fragile to the unknown hazards. And David Woods has done studies of many things, including looking at Amazon Web Services, and when they've had these huge outages with their data centers, where all of Europe would get knocked out, or all of the Western United States. And these systems, again, are extremely highly optimized. They have put all kinds of careful engineering into them with redundancies and so on, and they still fail, and fail catastrophically. And it's because there was some novel combination of things that occurred that was an unknown hazard, and the systems are fragile with respect to those. In fact, one of the things that's particularly difficult is often they don't have the appropriate logging to even detect exactly what went wrong, right? Because if they had known to check for things, they would have done that, and they would have anticipated it. And so in some of the cases he's analyzed, there are multiple people in different parts of the organization that if they could just be talking to each other, they could figure out what happened. One guy made one change, someone else made another change, and it was the combination that led to a problem. In any case, David Woods says that the only solution is to try to build a human organization that is poised to adapt, that can be dealing with these surprises quickly because it has practiced communicating across the organization. It has practiced doing this root cause analysis, trying to understand the origins of problems, and then to plan workarounds and confront the novelty. Now again, as an AI person, the perspective I bring is when we think about a design space, right, we think about an entire space of possible designs, and we know the particular design that was built followed some decision-making path through the design space and produced the design. And so what does it mean to be poised to adapt is that ideally we would keep the entire design space and design process on a sort of standby state so that we could, in the face of novelty, roll back and follow a different path in the design space and say, oh, we need to revise our design now to be this different choice. And so again, to the extent that, I mean, this is consistent with a lot of the things design people like to say, you know, we should be understanding the rationale for the current design and documenting the entire design process. But it also suggests that perhaps we could build AI tools to help with that. And I think we've seen, again, some of the company presentations today had some hints of this in the sense that companies have a lot of documentation for this. And so some of the tools that were being discussed would really help with this. Okay, so in summary, machine learning and traditional safety engineering are focused on managing known hazards, but machine learning technology and methodology as it currently exists is not able to do that. So we need to, of course, we need to support high-fidelity simulation, and we do see so much work now on digital twins using machine learning to build and validate them. But then I think we need to adopt these risk-driven generation of the training data and the test cases. And we need to develop some way of verifying the quality of our machine learned models. And I would like to see if we can achieve, if we can get away from the statistical machine learning and get to something that's much more like a distribution independent guarantee on the quality of our machine learning systems. And then I also mentioned this important sampling approach to estimating the probability of harm. So I think really it's this one that is the big one that we don't know how to do at all yet. For the others, we already have good examples to draw on. And then I talked about Leveson's view of safety as control, that you don't build a system and then deploy it and you know it's going to be safe. You have to be constantly controlling it to defend it against the disturbances that come from both the world operating environment and the institutional environment that you're operating under. And finally, safety as a form of resilience, building systems that are poised to adapt. And I think AI can help in both of these to some extent. AI can give us anomaly detection and near-miss detection for the safety as control. It can perhaps help with the diagnosis quite a lot, and maybe with the repair a little bit. And if we can use AI tools, if we're using AI tools during the design process, we should be able to use them during the repair process as well. So I will stop here and answer questions. Thank you very much.
Any questions?
Good.
Virginia?
Hi, thank you for your talk. Can you hear me? Can you hear?
Yeah, yes.
Yeah. 2 points. One on the near misses. It's not. I think it's a bit more than just the misses, but also the way that the society in general adapts to the new technologies. I had to think about talking about self-driving cars with kids in middle school, and there is not so much that they will stay away from the car if they think the car is colliding with them, but they see right away a kind of a game in which they say, oh yeah, a car is going to stop, so let me see how close to the car I can cross the road for the car to stop. So it's really a whole change that it's not only the near misses, but also the near opportunities, if you want.
Yes, the dares, yes. I mean, I've seen pedestrians do this in Mountain View, California,
yep.
And they weren't children.
No, okay. And the other one is very much connecting to this bridge between current machine learning models and what we would like to have for safety engineering. I had to think while you were talking about in safety engineering, actually what we want is to build some Lego construction in which we know for each of the small blocks exactly how it works, how you can put them together, which color they have, and so on. Current machine learning models and approaches are much more like Play-Doh. You put it all together, you mess it so much that you don't even see the colors anymore, and then you try to combine both. So I think that it's more than just putting them together, but it will fundamentally require a different way to design machine learning systems if we want to put them to use in safety engineering.
Yes, I'm very confused about this right now, because I have always thought exactly what you thought, which is that if we're going to be able to understand the design, it needs to be modular with very clean interfaces, and then we can see what's going on. We can diagnose which component made the mistake. We can fix that component, and so on. But the people at Wabi are now taking an approach that's different. So the traditional approach when you're using computer vision in these kind of applications is first we do object detection. So we detect the bicycle and the pedestrian and so on. Then we do object classification. Is this a stationary obstacle, or is this something that's going to be moving? And then we do some sort of prediction, and then we do planning to plan a trajectory. They're taking an entire end-to-end approach because they're trying to avoid the accumulation of mistakes that are made at each of those phases. And so they are not modeling individuals. They're actually trying to do prediction directly from the LiDAR maps. And it makes me very nervous. I sort of see why they're doing it, and I don't. So I guess we'll see whether they can really make that work. But I'm very sympathetic to your perspective, because then when something goes wrong, was it something with the LiDAR, or was it something? Yeah.
I'm looking forward. Very interesting. Yeah.
Yeah. Okay. There's some questions here in the front.
So I work in mining, and big autonomous trucks going around mine sites. It seems to me you're tackling a really tough problem. You're trying to work out what pedestrians. Sorry. So I work in mining.
Yes. Yes.
So we're putting in a lot of autonomous trucks.
Yes.
And we have these lovely places where no one's allowed to go in unless they're controlled when they go in.
Yes.
Everybody does safety shares. You're trying to do a really tough problem, right? Because you're trying to deal with autonomous vehicles out in the world.
Mm-hmm.
How are you doing on mining? What systems have you, because that's a nice, easy problem.
That is a good question. And I have not read much about this, but I know particularly in Australia, they have these huge automated mines, and I mean, I would guess there's still problems that people get in there, and one of the, I think AI and computer vision in particular have raised expectations within the automated sort of driving community that we can do things that maybe we cannot do. So most of my research in the last 10 years has been this so-called open category problem. I had to skip the slides, but how can we build a system that can detect that it's looking at something it's never seen before? And part of the problem there is that, well, if we can hand engineer the representations, we have very good anomaly detection strategies that can deal with that. And in fact, I'm involved with Big ML. It's one of the sponsors here. And we've had a big success at Mercedes in manufacturing line anomaly detection, right? We have a lot of engineering expertise we can apply. But for deep learning, the power of deep learning is that it learns its own features. But the weakness of that is we don't know whether those features are any good for anomaly detection, because the deep learning system only learns the features it needs to learn to perform the task. And we can see that often those features are not rich enough to detect new things that it hasn't seen before. And there was a fun story you may have heard for Volvo sells cars that have this deer detection system, and they took it to Australia and it failed because kangaroos don't behave like deer, and so it was a good example. I just made up an example like that to use in my lectures. I was shocked to find out it was actually a real case. So I think there is absolutely no guarantee that we can always detect novelty, right? Suppose there are aliens right here in the room, but they're only visible in the ultraviolet. We lack the sensors to detect them. It would be tricky. Maybe they smell, I don't know. Anyway, but I think if we take a foundation model approach to computer vision and we train on as much variation in the world as possible, we will learn extremely rich representations. And then the hope is that something novel we will have a way of representing it in our representation space, and it will be some kind of an outlier that we'd never seen before, and so we will detect it. It's not a guarantee, but I think that's the most practical strategy we have right now. Traditionally, we have trained our computer vision systems to say, well, here are the things we want to detect, let's train on them. But now we're going to say, train on everything else you can imagine. In fact, hire Joan Miro or whoever to invent things we've never even thought of, and let's train on those as well. We just would like to get lots of synthetic variety as well. And hopefully that will cause the deep learning systems to learn good representations.
Professor Dietterich,
yes.
Thank you so much for your talk. In principle, well, my question's in part already been answered, I think, with what you just said. The last part, when you start about talking basically distribution independent generalization, I thought, how on pixel level are you going to cover the whole space, right?
Yeah.
Then you were talking about this example with the 50, I think, latent dimensions, which sounds on the other side very little to cover all these possibilities, right? And then I also thought about foundation models as this very rich representation. And I mean, you probably know about this topic mapping, what people have been doing now with the LLMs, where they found, okay, here is basically encoded, I don't know, PISA, right? Where they then manipulated basically facts with this knowledge of where what representation is. I was just wondering if you see some chance in this direction with multi-model foundation models that you could basically, let's say in this example with, I think India, where they had these different signals, like the triangle.
That was Peru, yes. But
where they basically just substitute certain pieces of the data.
Right.
Where we now understand sort of, in the latent space where these things are.
I think yes. I don't know. We should probably talk more offline.
So thank you, Professor. Really impressive presentation. How to, in 45 minutes, make all this historical analysis for all the adaptation for safety and cyber resilient equipment. My main question, my background is IoT, Internet of Things, embedded system. So my main question and my main worry is about how to guarantee this kind of poised to adapt in very constrained systems with embedded equipment, because for me, for example, in my real experience, and I would like to know your opinion, for example, when I have very good models working, developed by my team, but when I try to adapt it, for example, for tiny ML, finish. Right. That's a scale. So then my big question here is, what is your opinion about tiny ML as all this equipment will require some kind of embedded? How you envision the future of embedded machine learning, like tiny ML? And my second question following that, could be federated learning a solution for that, or doesn't really imply having these kind of small pieces of machine learning working or cooperating together, a way to make it scale it up when you need to really afford safety, but also very constrained environments?
Those are very good questions. I've usually thought of federated learning only during the training process, but maybe we should think about it in this kind of anomaly detection case. So if we can pre-train really good representations, maybe we can bring those down to the edge without having to, and just train an encoder to take the input signals and embed into those representations. Maybe we can still do good anomaly detection at the edge. But then the other kind of reasoning about what to do about that, maybe that does require having hubs and a hierarchy of computation. That if the edge system says this looks unusual to me, then I need to pass it up, maybe or to maybe peer to peer, but I need everybody to look at it and see, well, if we use a more higher dimensional, deeper representation, does it still look like an anomaly? And maybe we can do something like that. Use a sort of nested filtering with low thresholds at the edge, and then the thresholds get higher and higher as we go deeper into
It's like
the
we
system.
call it here the computing continuum. Like
Right. Yeah. Mm-hmm. So yeah, that's a really good question. Yeah. I mean, of course, I always worry in federated learning about cyber attacks now, because you expose all these new surfaces to being attacked. All the communications in between in the federation is
because
at
my
risk.
analysis that we realize today, even with GPT and all these language models and all the AI power,
Right.
I think it's clear that the AI power is huge, but the big challenge today is how to bring and adapt these huge AI capabilities, for example, for embedded devices, smartphones, etc. For example, when Meta tried to make an algorithm, their worry is not to make a nice face recognition algorithm. The worry is to make it worse in a smartphone.
In a small package.
And a small battery. That is the big challenge. And
Right.
that is the kind of problem that we are also having when we go to connected vehicle, electric vehicles and connected vehicles, because at the end of the day, the embedded system running there are not so powerful, are not so adaptable, must be 10 years lifetime technology.
Right.
So this is a huge challenge for adapting ML.
Right, and here I am saying, oh, you should add more sensors to look for near misses and anomalies. And of course, the size, weight, power people are saying, we don't have any additional space to do that. Yeah, so I guess it depends partly on the time constants involved and the severity of the faults. I mean, one thing that I was thinking in these hydro applications is that you have a lot more time, more on the order of hours rather than milliseconds, to say, oh, we think we have a flood coming, or we have some sort of a fault in a water line. I don't know. I don't really know what those time constants are, but it seems like you would have more time to think about mitigations and alternative strategies. So you might not need to have all that intelligence at the edge to do that.
Correct. Right now in Europe, because we love to create regulations
Yes.
for everything, Data Act, AI Act, now we have what is called the Cyber Resilient Act. And this is quite cool because it's actually defining the different level of categories of cyber resilience, including AI capabilities for different equipment. And it's quite interesting because, for example, of what you are presenting here for cyber resilience and for these safety environments must be addressed by the CRA. And this is quite competitive because it's the way Europe try to compete with also other emerging markets, try to put cyber resilience as a key mandatory requirement.
Right. Yeah. Well, thank you very much for those questions and for your attention.